Hello, everybody. I hope you are doing well. So, week 14, session 3. This is the last presentation in this week, week 14. So, we'll go over the previous lecture and then we will solve two examples from auto cycles. Uh, so if you remember, we discussed the Otto cycle in the previous lecture. Otto cycle is the ideal cycle for spark ignition engines. So the diesel cycle is the ideal cycle for compression ignition engines. So we actually this week we discussed the Otto cycle, and then next week we'll discuss the diesel cycle. So for the Otto cycle, if you remember, it has actually four steps. It includes two isentropic steps and two constant volume steps. So the first step, there is an isentropic compression. So V1 is actually the Vmax in the process. V2 is the minimum volume in the process, and then process 1 to 2 is the isentropic process. And then at constant volume, heat is added to the system. So we have a constant volume heat addition from point 2 to 3, or process 2 to 3. And then there is an isentropic expansion step from state 3 to state 4. And then eventually heat is rejected at constant volume. So from point 4 to 1. Keep in your mind that this actually process, this cycle, this Otto cycle includes 2 revolution and 4 strokes. So to calculate the thermal efficiency of Otto cycles, there are two actually options. If you assume that we have variable specific heats, then you are only allowed to use this equation to find, the thermal efficiency of Otto cycle, which is W net over Q net, or 1 minus Q out over Q in. Keep in your mind that the Q out is actually Q2 to 3, Q 4 to 1, and Q in is actually Q2 to 3. So if you assume that you have a constant specific heat, then you can use one of these three equations to find the thermal efficiency of Otto cycles. So T1 is the initial temperature, and the T2 is, the second temperature or the final temperature in isentropic process between point 1 and point 2. And or you can use this equation 1 minus 1 over R K minus 1. Keep in your mind that R is the compression ratio, is the ratio of the Vmax over Vmean, and then Vmax is actually V1 and the Vmean is V2. So if you have the constant specific heats, you can use one of these three correlations to find the thermal efficiency of Otto cycles. So I highly recommend you guys to plot the TS and PNU diagram to solve problems of chapter 9. These two diagrams are really helpful. They help you guys to just manage, your information, and also find the best method to solve the, problem. So if you look at the TS diagram, this is a TS diagram, for an ideal Otto cycle. For the Otto cycle, you can see that we have two constant volume, steps, and two isentropic steps. So based on this, figure, the first thing is that the, T1 is the minimum temperature in the process, and then T3 is the maximum temperature in the process. Also, based on this figure, we can write S1 equals to the S2, and then S3 equals to the S4. So if you plot the PNU diagram, this is the PNU diagram, for the Otto cycle. Again, you can see two isentropic process steps and two constant volume steps. Based on this, PNU diagram, you can see that the Vmax is V1 and the mean is V2. Keep in your mind that based on this, figure, V2 equals to the V3 and V1 equals to the V4. So again, guys, I highly recommend you to plot the TS diagram and PNU diagram to solve, the problems of this, chapter. The other thing is that, guys, we have two isentropic, steps, in this actually cycle. If you remember from the previous chapter, we developed some correlations for ideal gas with, actually for isentropic process with ideal gas. So if you remember, for isentropic process with ideal gas, if we assume that we have a constant specific heat, we can use these three correlations to find, actually to relate temperature to volume, temperature to pressure, and pressure to volume of, ideal gas, in actually isentropic process. So if you assume that you have a constant specific heat, you can use this correlation. Keeping in mind that K is the, a specific heat ratio. So if you assume that you have a variable specific heat, then you actually can use, these two correlations to find, temperature, pressure, or volume of, ideal gas with variable specific heats in isentropic process. Keep in your mind that the PR and nu R are relative pressure and relative specific volume, and then you can find these, parameters from the, tables, reference tables, thermophysical property tables. Okay, so look, guys, we have three types of actually, equations, to solve chapter 9 problems. The first part is, these equations. You need to pick, the right equation depending on the, variable specific heats. If you have a variable specific heat or constant specific heat. The second part, you can actually use, the correlations from chapter, 7 to find, temperature, volume, and pressure, for isentropic process, for process between point 1 and point 2 and point 3 to point 4. And then the third one is that, guys, you can write the first thermodynamics law for, each process. Keeping in mind that you have four, process in this cycle. So two isentropic process and two, constant volume process. So you can write the first thermodynamic law, for each step of this, process. This is, another type of, equations that can help you guys to solve these, problems of chapter 9. So you can write Q net minus W net equals the delta U. And the final thing is that, guys, by using, this correlation, you can calculate W, work. But in most cases, guys, we are interested in the power. We need to calculate the power of, for example, engine. So this, you can use actually this correlation to relate, power to W, to work. So if you calculate W from the, these correlations, then by using the n dot, which is revolution per second, and n, which is the number of revolution per cycle, you can convert, work to the W. Keep in your mind that, guys, for Otto cycle, the number of revolution per cycle is 2. There are 2 revolutions per cycle, so n is 2. Okay, this is a short, actually summary about the previous lecture. I just try to, organize the equations. And now let's solve 2 examples, from this part. The first one is, simple, problem. So we have an ideal Otto cycle. So we have the compression ratio. The compression ratio is 10.5, and then we have some information. First of all, I recommend you guys to plot the PS or PNU diagram. In some cases, you may need to plot both these two, diagrams. So here, let's plot the PNU diagram. So this is the PNU diagram, typical, PNU diagram for Otto cycle. So we know that the initial pressure is, 90 kilopascal. So we have the P1 and T1, correct? Both P1 and T1 are known. I highly recommend you guys to convert, the temperature to the absolute temperature. So because if you want to calculate the thermal efficiency by using that equation, thermal efficiency equals to 1 minus T1 over T2, temperatures must be absolute temperature, guys. So I highly recommend you to convert this temperature to the absolute temperature. So this is the first step, and then I just transfer temperature and pressure to this diagram. So we have the N dot. The N dot is 2500 actually revolution per minute. So keep in your mind that you need to convert this revolution per minute to revolution per second. So you need to divide it by 60. And then you are asked to use the constant specific heat at room temperature. And then determine the thermal efficiency of this cycle. So uh, and also that the power is the net power is 90 kilowatt. So we have the compression ratio. So the compression ratio is 10.5. Based on the definition, the compression ratio is the V max over V mean. And then in this actually diagram, you can see that the V max is the V1, which is equals to the V4, and the V mean equals to the V2, and then V2 equals to the V3. So, and then these are, the, other available information, and then you're asked to calculate the Q dot in. Please pause this video and then just spend 2 minutes and then find the best equation to calculate, the thermal efficiency, and then calculate the thermal efficiency of this auto cycle. Okay, guys. So to find actually the best equation to find the thermal efficiency, let's go over all available equations to find the thermal efficiency of Otto cycle. So here we have the constant specific heat. So you need to pick one of these three equations. So based on the available information, because you have the R is available, the compression ratio. You can find K from the reference tables. K for air at room temperature is 1.4. So you have R, you have K, you can simply find the thermal efficiency. Then by having the thermal efficiency, and then you have the W, you can find the Q for, this system. So here, we have, you need to use this equation. K is 1.4. You can find the thermal efficiency, which is 61%. And then by using this value, you can find the Q dot into the system, which is 140 kilowatt. Okay, so for the second example, please open the guided note file available on the Blackboard. So in this example, you actually ask to there is a problem for a 6-cylinder 4-stroke spark ignition engine. And then so we have some information, guys. If you look at this problem, you can see that we have several pieces of information. I highly recommend you guys to just as the first step plot P nu and the TS diagram. So I just canceled, guys, that table. If you remember, normally I just ask you guys to add information to a table, but I believe that for chapter 9 it's actually more convenient to just transfer all information or available information to the P nu and TS diagram. So please pause this video, spend 5 minutes, and then transfer all available information for in this problem to a PNU and TS diagram. So first plot PNU diagram and TS diagram. Then I recommend you guys to just draw a simple piston cylinder device, because we have some information for the piston and cylinder, and then add all available information to this figure, and then just mention and what is the unknown parameter. So pause this video, spend 5 minutes, and then just find all available information to solve this problem. Okay, guys. Now, so Before we solve the problem, guys, we need to actually find the thermophysical properties as well. So, what is the thermophysical properties, guys? Look, you are asked to use the constant specific heat at room temperature. You look the last line, use the constant specific heat at room temperature. So, you need to find the K, a specific actually heat ratio. You need to find the CV, and then also you need to find R. You know, the ideal gas constant. Please pause this video, spend 2 minutes, and then find this um, thermophysical properties. Okay, guys. So the next step is step 3. You need to find the W net. So to find the W net, you need to actually uh, just list the best equation to find W net, and then you need to just find the other unknown parameter, and then eventually you can find W net. So to solve this part, guys, let's go back to my presentation file. Okay. So this is the next actual, example. So the first step, I just ask you guys to plot the TS diagram, PNU diagram, and it's actually piston cylinder device. Look, guys, if you plot this, two diagrams, you can simply add available information. So we know that this is a 6-cylinder, 4-stroke, and spark ignition engine. It's we need to use the ideal auto cycle. So in air at 14 psi and 105 Fahrenheit. So these two pressure and temperatures are, inlet pressure and temperature. So we have the P1 and T1. Again, keep in your mind that you must convert this actually, temperature to the absolute temperature. So you need to convert the Fahrenheit to the, absolute temperature. And then you have the maximum temperature of this cycle. Look, guys, if you plot the TS diagram, you can simply see that the maximum temperature of this cycle is the T3. So we have the T3 as well. Again, T3 is in Fahrenheit. You need to convert it to the Rankine. Then we have some information for the cylinder. We know the bore is 3.5 inches, and then stroke is 3.9 inches. And then the last thing is that we know that the minimum enclosed volume is 9.8% of the maximum enclosed volume. Or we can write the V2 equals to 0.098 times V max, which is actually V1, correct? This is the relationship between the V min and V max. So you are asked to find the power, W dot, and then we have the RPM at 2500, and you asked to use the constant specific heat at room temperature. Look, guys, we have actually this relationship between V min and V max. If you use the definition of R, you can find the R, the compression ratio. What was the definition of R? The definition of R was R equals the V max over V mean. If you substitute, for the V mean from this equation, you can find the R, correct? So R equals the V max over V mean. So if you substitute for the V mean into this equation, we can find the R. So the compression ratio is 10.2. We have also the compression ratio. Now, this is all available information, guys. Keep in your mind that we have also, the RPM, and we know that this is the 6-cylinder. Now, the next step, we need to find the thermophysical properties. So we need to find the R, CP, CV, and also the K from the reference tables at room temperature. Now, the next step, guys, what is the unknown parameter? So the unknown parameter is W dot, power, correct? How we can calculate the power? I told you guys, by using equations that we learned in this chapter, we can find W. Work. So we need to convert actually W to the power. How? By using this equation, correct? So to find the power, you need to have the work N dot and N and the number of revolution, correct, per cycle. So you know that the number of revolution per cycle for auto cycle is 2. This is known. N dot is now, we know that the N dot is 2500, RPM. You need to convert it to the actual, revolution per second. So you need to divide it by 60. What is the W? W is the total W, guys, which is W per unit mass times mass. So what we need to do, guys, we need to calculate mass and W. These are the two unknown parameters. So the unknown parameters are W net and M. We need to determine, the W net, work per unit mass, and mass. Okay, so to actually calculate, W, let's, check, the available equations. So here, you can see, all equations for the thermal efficiency of Otto cycle that you learn in this chapter for Otto cycle. So for the variable specific heats and constant specific heats, here you are asked to use the constant specific heats. So you need to pick one of these three equations. So look, guys, R is known. You calculate the R. Correct? The compression ratio is R. You found K from the reference table. So by using equation 3, you can simply find the thermal efficiency of an Otto cycle. So you have the thermal efficiency of the Otto cycle. If you use the first equation, you can actually find the W net. How you can find the W net, guys? You can actually find the Q in. If you write the energy balance for process between point 2 to 3. So if you write the energy balance, the first thermodynamic law for process between point 2 to 3, you can find the Q in, and then by using the equation 1, you can actually find the um, uh, W net. So again, guys, what you need to do, you need to find the thermal efficiency from the equation 3. Then you can find the Q in from the first thermodynamic law, and then by using the first equation, you can find the W net. Please spend 5 minutes, guys. Pause this video. Now you have all information, all equations, and then try to find the thermal efficiency, then Q in, and then eventually W net. Keep in your mind that this W net is W per unit mass. Okay, so look, guys, we have the R. R is 10.2, K is known, it's 1.4. Keep in your mind that K is unitless, it's a ratio of two specific heats. And then from here, we can find the thermal efficiency. So the thermal efficiency of Otto cycle is known. Now we can actually use the first equation. Based on the first equation, the thermal efficiency is the W net over Q in. So from here, we can actually write the W net equals to 0.605 times Q in. So we need to find the Q in to find the W net. So to find the Q actually in, you need to write the energy balance for process between point 2 to 3. Keep in your mind that this all process actually in Otto cycles are closed system. So you can write Q net minus W net equals to the delta U. We normally assume that the changes in kinetic and potential energies are negligible. So Q net minus W net equals to delta U. So here for this actually process between point 2 to 3, if you look at this P diagram, you can see that the volume is constant. So there is no W shaft, there is no electrical work, there is no boundary work. Why? Because the volume is constant. So there is no W, guys. You can cancel W. So you can simply write Q net equals the delta U. And then Q net is Q in minus Q out. For this process, Q out is 0. You can simply write Q in equals the delta U. Keep in your mind, guys, because you assume that there is a constant, that constant specific heat actually assumption is valid. So you can write delta U equals the CV T3 minus T2. Again, guys, if you are asked to solve this problem by using, the variable specific heats, you can't write, guys, you are not allowed to just to write, this equation CV T3 minus T2, correct? So you should write Q in equals the delta U. However, in this problem, you are asked to use the constant specific heats. Sorry. So you can write Q in equals the CV T3 minus T2. So you found the CV from the reference table. T2 actually, T3 is known. T3 is the maximum temperature. And then what you need to do, you need to find the T2. How? Please pause this video, spend 3 minutes, and then try to find T2. Okay, guys. So to find the T2, if you look at, the PNU diagram, you can see that the process 122 is an isentropic process. So the T1 is known. You have actually the ratio of V1 over V2. So you can use this equation to find the T2. You can write T2 over T1 equals to V1 over V2 to K minus 1. V1 over V2, V1 is the Vmax, V2 is the Vmin, and the V1 over V2 is actually R, compression ratio, right? So from here, you have everything. You can simplify the T2. Now you have the T2, you can substitute into this equation to find the Q in. And then Q in is 244.41 BTU per pound mass. Now, if you substitute this value into this equation, you can find the Q net, sorry, the W net. Now, so look, guys, in this actual problem, R was known, and then we simply found, the W net by using, the R. Correct. First, we found the thermal efficiency, and then from the definition of thermal efficiency, we found the the W net. In some cases, guys, R is unknown. So you should be able to calculate, the W if R compression ratio is unknown. So what I'm going to do, guys, I'm going to solve this actually part. I'm going to find the W net by the second method. And then without using the R, compression ratio. So this is the first one, guys. You are right. You actually find the W net. However, in some cases, in some problems, you don't have R, the compression ratio. So I'm going to show you the second method to calculate, the W net without using this R. So if you want to use the W net, you can actually use the first thermodynamic law for the Otto cycle. If you write the first thermodynamic law for the Otto cycle, this is the Otto cycle. Actually, this is a cycle. You can write W net equals to the Q net. So we are looking for the W net. What is the Q net? Q net is Q in minus Q out, correct? And then Q in is Q2 to 3, and Q out is Q4 to 1. So you need to find Q2 to 3 and Q4 to 1. So how? By writing the energy balance for our first thermodynamic law for process between point 2 to 3 and process from point 4 to 1. So if you write the energy balance, guys, for the first one, for the actually process 2 to 3, I explained you guys that this is a constant volume process. There is no W shaft. There is no electrical work. So you can simply write Q net equals the delta U, or CV T3 minus T2. If you write the energy balance for process 4 to 1, correct? So again, this is a constant volume process. There is no electrical work, no, W shaft, and then boundary work is also 0 because volume is constant. So you can write Q net equals the delta U. What is the Q net? Q net is Q in minus Q out. For this process, Q in is 0. So we can write negative Q out equals the delta U. Or this is equals to CVT4 minus T1, correct? This is actually CVT1 minus T4. However, if you just multiply this negative value, you can write Q out equals to CVT4 minus T1. So to find actually, the Q in and Q out, you need to have the T2 and T actually 4. Correct? T2 and T4. We already determined the T2. So please pause this video, spend 2 minutes, and then try to find the T4, temperature for point 4. Okay, guys. So you actually can use the same equation that you use to find the T2. Keep in your mind that so process between point 3 to 4 is an isentropic one. You can write T4 over T1 equals the V3 over V4. V3 equals the V2 equals the V mean, and then V4 equals to V actually 1 equals the V max. So V3 over V4 is actually 1 over R. Correct? 1 over compression ratio. You have the compression ratio and then you have the T3, you can find T4. Now you have all information, all temperatures, you can simply find the W net. If you just substitute these values, guys, and use the CV equals to 0.171 BTU per pound mass Rankine, then you can find the W net. Look, guys, the W net is exactly the same as the value that used by the other method, correct? So this is the W method by using two different, methods. Keep in your mind that, guys, again, in some cases, our compression ratio is not available, and then probably you need to use, this method. Or you may have, the R, but, you prefer, for example, to use, this method. Okay, so now we found W. What we need to do, we need to find mass of air in 6 cylinders. So to find the mass of actually air in the cylinder, we have some information about the dimension of this, piston cylinder device. So we have the diameter of this, cylinder, and also we have the S, the, stroke value. So from here, guys, we can write the delta V equals the pi b square times s over 4. What you need to do, you need to convert actually these inches to feet. So from here, you can simply find the delta V. Now you have the delta V for one cylinder. If you multiply it by the number of cylinder, you can find the total delta V or the total volume, correct? So the total volume is n number of cycles times delta V. Now you have, guys, the V total. What's the relationship between V and mass? We can write M total or M equals the V total over nu 1, a specific volume for actually 0.1. So you can actually find the new one. How? By using the ideal gas equation of S-net. Please pause this video, spend 2 minutes, find new one, and then from the new one, find M. Okay, so from here you can find new one, and then we can find M. This is the M total. Now we have the M, we have the W per unit mass, and then from here you can find the total W, and then eventually you can find the power. So here, guys, in this example, we just go over, problem with constant specific heats. In some cases, you may need to use the variable specific heats. So in these cases, if you need to solve the problem with variable specific heats, keep in your mind that there are three main differences between this problem that I solved by the constant specific heats and problems with the variable specific heats. The first difference is the equation for the thermal efficiency. if you have problem with variable specific heat, you are only allowed to use this equation to find, the thermal efficiency. You are not allowed to use, those equations, based on the temperature and, or compression ratio. The second difference is the first thermodynamic law. For problems with constant specific heat, you can write Q net minus W net equals to the delta U, which is equals to M CV times delta T. Correct? However, for variable specific heat, you are not allowed to use, the CV. Correct? You should write, the Q net minus W net equals to delta U, or this is equals to the M times CV average. You need to find the CV average times, delta T. Correct? So if you have two actually options, you can find the internal energies, or you can use the average specific heats, to find the, at the right side of this, equation. And then the third difference is the isentropic process. We have two isentropic process. So for the isentropic process, for process 1 to 2 and 3 to 4, you need to use these two correlations to relate pressure to pressure, volume, and temperatures. These are three main, differences between, problems with variable specific heats and constant specific heats. Please study example 9.3. Example 9.3 is an example with variable specific heats, and then we can simply see, the differences between, problems with constant specific heats and variable specific heats. Please study example 9.1, 9.2, and 3. Thank you so much, guys, and have a great day.